by the way, which should launch the YouTube. And then I will have that URL from YouTube here in just a second.
I would prefer to be there in person.
Okay.
Too many distractions at home.
Yeah, there's some truth to that, right? There's also a lot of you, that are maybe like commuting down from Salt Lake or, and all of a sudden you're just getting back, hour and a half to 2 hours every single day. Okay, there's the link. Here's the link. Walter, you mind dropping that bad boy into the schedule? I would be most appreciative if you could do that. Thanks, man. Okay. All right. I'm ready. I brought with me today ice packs to just shove under my butt and stick on my back and put it under my leg and whatever else I got to do. It'll help me to get through. Yeah, Cody, I actually, the truth is I like this class a lot online. Honestly, I've only got a 20-minute commute, 15 to 20 from Lehigh right now. But I'd just rather not, have to go drive somewhere to be someplace in person. Although being in person, there's a lot more kind of human contact. Get to know you better, get to know your face. It's better. Big advantage. Okay, friends, let's do this thing. Let me see. Yeah, Junker, man. Streaming to be an option, but back in class, I'd love to find some kind of a hybrid. In fact, I've been actually recording, even when we were in class in person, I was recording lectures with a video camera, and then I would post those lectures on YouTube. You can go back on my YouTube channel and actually see lectures from me teaching this stuff in the classroom setting. And I just Velcro strapped an ice pack onto my leg. Hopefully that works. So if you're wondering what I'm like wrestling with over here, that's it. Okay, let's do it. Let's do it like we mean to do it. Here's where we got to. Was it feeling pretty fast last time? I kind of have the impression that it was feeling pretty fast for everybody. I don't know if there's a great way around that. You got to take some time to go through it, acquire that fluency. Cold pack. Here we go, baby. Here we go. This ought to help cut some of the pain. Yeah, it's helpful. We were talking about multiplexers. What's really interesting about this is as we get into these structures like decoders and multiplexers, and what was the last one we were going to do? I don't remember. Adders? I can't remember. We're going to get there. We really are. The really kind of cool thing is we really are simply continuing to make use of the same old structures, the very same structures that we were doing for you notice they're the same old circuits, same old things, wires and gates. And if you want to double click on this conceptually, right, every one of those AND gates, you can kind of blow it up and get it all the way down to the transistors if you want to do that, right? But it's all built out of the same material. What's the other one we were going to do? Yeah, adder, okay. Remember what a multiplexer does. Best way to remember it is, 3 cars all coming up to an on-ramp during rush hour, and there are 3 lights, and 2 of them are off and 1 of them is on every time. Then it switches, and now there's a different one that's on and the others are off. That's exactly how a multiplexer works. This one, just remember, is crazy simple. I got 2 inputs, A or B, and I can select either A or I can select B. Okay? When I call it 0, when the select is 0, I choose A, and when it's 1, I choose B. Okay? So that's kind of our reminder. This is just an example of let's do one with 4 inputs. So imagine it's a bigger city, I don't know, whatever it is, it's LA or it's some larger city. I'm sure that there are cities with 4 on-ramps of 4 lanes, 4 lanes coming in and there's only 1 going out, right? Well, I got A, B, C, and D. Ooh, I got to do another thing. Sorry. Sorry, I have a little space heater right here. My office gets, for some reason, I think it's just poorly insulated or something, but it's cold in here. So I had to turn on that little space heater. And it's not just because I have ice packs all over my body now. Okay, I got 4 values coming in, A, B, C, D. Which lane is going to go? Well, the notation here is S, and then it's like 1:0. That's just a notation to say that the first line is 1 and the second line is 0. Viewed another way, the value of S could be 0, 0, 0, 1, 1, 0, or 1, 1, which gives you 4 values, right? 4 possible values. How many lanes are there? 4, lanes, numbers, A, B, C, and D. And you can map it yourself. Take a look. When they're both 0, when both lines are 0, you can see that A is going to be on because those 2 zeros are both going to be turned into 1s. And when those are both 1s, whatever A is coming through. If A was a 0, it's going to be a 0. If A was a 1, it's going to be a 1. Whatever A is comes through. What does B have to be? Well, it would have to be 0, 1 to be B, to activate B. And that same 0, 1 pattern will cause all of the other ones to force a 0 at the bottom. Okay? Same thing here. It would have to be 1, 0, and this would have to be 1, 1. So you can see that the selector lines essentially are just counting from 0, 1, 2, and 3. They're counting 4 values from 0 to 3. And each number turns on a different AND gate. Isn't that cool? That's fairly cool, is it not? Dr. K asserts it is cool. Dr. K asserts you should also think it's cool. Oh, hang on. And Dr. K also is a dummy who forgot. Ready? Oh yeah, Rockstar. Here we go. Yeah, I forgot my light up. I was going from the dank light of the shade and the shadows like we used to. There's my better light. Then I have to get my glasses off, my reading glasses off, so it doesn't blind everything. Okay, what else is going on here that you can see? Then all 4 of these lines funnel into this OR gate. So now you've got an AND gates with 3 values coming in, the original value and the selectors. And then you've got all 4 of the outputs of those AND gates coming to the single OR gate. Cool. And what you notice is, let's just take this example of S1 and 0. So the first line is 1 and the second line is 0. That's going to turn on C, right? You can see that, can't you? That C is the one that's going to turn on. And all the others are going to be turned off because there's going to be at least one of the 2 values is going to be 0, which means the AND gate is going to go nope. When 0 hits an AND gate, it just blows it up. Okay? So when it's 1, 0, then the first line goes 1. The 0 hits this knot and turns into a 1. So I can tell that C is the right value. So it's going to be 0, 0. Whatever C was, 0. You're going to OR those together, and any zeros coming into an OR gate doesn't really matter. The only question is there a 1 or is there not? So if C was a 1, you're going to get a 1. And if C was not a 1, you're going to get a 0. But bottom out, this bottom side, you're going to get whatever C was. Rock and roll. And then this is the notation. We remember before we did, this is a little trapezoid, right? There's the values coming in and an output coming out on a selector. Okay. Well, what we do is we have a new notation where we can take those lines, you put a little slash through it, and like /1 says there's 1 line. /2 says there are 2 lines. Okay, and you can do this all the way up to 8, 16, 32, 64. Okay, so you've got A, B, C, and D coming into the multiplexer, a selector line with 2 lines, and an output, which is 1 line. All right, any questions? I think, yeah, that's all. That's the, we did a little more here, and now we just, you see how it's the same concept, only S got bigger? Well, so, okay, question for you then. If I had 16 values, how many S lines do I need to have? Hang on a second. Junior, why would it turn on C? Let me back up before I do Alex's response. So, Junior, you thought it would turn on B. This 1, 0. So this first line is a 1. Let's try B. Let's look at. I could have said it wrong. I could have said it backwards. This top line is 1. Okay, let's go to do B. Okay, all right, Junior, we good? If that guy's a 1, he hits the knot, and that becomes a 0. You put a 0 in any and it blows everything up, and it's just going to be a 0. Does that make sense, Junior? Whereas if you take that same value over here to C, you take the 1 coming in, and you drop it down, and okay, that's 1. You take a 0 coming in as the second value, okay? The 0 hits the knot, flips it, makes it on, and I got 1 and 1, and in every other instance, there's going to be at least a 0. Okay? Let me know if that's working. Okay, awesome. Back to so Alex answered the question, if I had 16 values, how many lines do I need for S? If there are 16, it's A, B, C, D, E, F, G, H, I. Suddenly I'm Nicolas Cage doing the alphabet in whatever that movie was. It's a classic. A, B, C. I don't know. I don't want to do a Nicolas Cage impression. A, it's difficult for me to do. B, it's not that rewarding when I'm done. Well, yeah, no. So Alex is correct, and half of you who thought it through and said 4 in your mind are correct. And then for the rest of you who either didn't think about it or said some other number in your mind, you're not correct. I would have 4 lines coming in. Okay. Again, back here I had 4 inputs, which was 2 to the 2, and that exponent tells me how many select lines I need. If I've got 16 inputs, what is that? That's 2 to the 4. How many input lines do I need? 4. Okay, that's the relationship, okay, that I need when I have 2 to the n inputs. Do I say this in terms of n somewhere? Right here I do on this slide, 41. When I have 2 to the n inputs coming in, I need n select lines. So if I have 64 inputs coming in, if I had 64 inputs, right? 64 is 2 to the, you can do it in your head if you need to. I always remember 2 to the 5th is 32. I don't know why. I always remember that. 2 to the 5th is 32. So to get one more, to get to 64, I got to double 32. So 2 to the 5th, it's 2 to the 6th. Okay? So, excuse me, if I have 64 inputs, that's 2 to the 6th. I need 6 select lines, right? Because I've got to be able to basically create the numbers from 0 to 63 to identify the 64 inputs, right? So I got to have something that's big enough to count that high. And what you're going to see, the other thing that's kind of a pattern you'll see, that we've got this is going to go 0, 0, 0, 1, 1, 0, and 1, 1, right? That's what the select lines are going to do. But also notice that if you look at these circuits here, there's a pattern. Look at just the knots, okay? Well, put it another way. What are the values that make D go 1, 1? What are the values that make C goes 1, 0? What's the value that makes B go 0, 1? What's the value that makes A go 0, 0? So if you look at just these gates, it goes 0, 0, 0, 1, 1, 0, 1, 1. They correlate. And that's because, the number 3 is going to happen to correlate with number D. So every number you can create with the select line is going to turn on one of those AND gates, and it will simultaneously turn all the others off. And I think that's cool. Okay, I'm going to keep going. Hang on, put your seat backs and tray tables in their full upright and locked positions. Make sure that all of your electronic devices are stowed and are in the off position, whatever that means. Okay, hospital mug for Diet Dr. Pepper, still cool. I don't mean cool to the touch, it is, but still like. Oh, and by the way, I'll have to show you next week. I'll show you my tricked out walker. I still have a walker. I can't safely walk a lot yet without the walker. I have owned it. And I have an absolutely tricked out walker that I'll share with you next week. I'll drop a picture of my walker, starting with the tennis balls. You know what I mean? If you're going to do a walker, by damn, you
Got
have
to
to
do
have
it from
some.
the bottom up, right?
What's that, Eddie?
Got to do it from the bottom up, right? It's all about
Absolutely.
abstraction.
Absolutely. And also, I've seen those old folks with those walkers, right? They always have tennis balls. And I just think, I'm relatively young to be using a walker, but if I'm going to have a walker, I'm going to have tennis balls, Okay. So here's what we're going to do. Remember when we did addition? 0, 0, 1, 1, 0, 1, 1, 1, 0, 0. I'm talking technology. Well, we can build a circuit. Basically, a circuit, it's just a circuit to count stuff, to count on up. If you think about it, the act of adding and the act of counting are kind of the same thing. Counting is really just a subset of the action of adding, right? Because if I go, okay, let's go 1, 2, 3, 4, 5. What are you doing in practice? You're just adding 1 every time. That's all you're doing is adding 1 as you count, literally. And then when you're counting in binary, okay, 1, 0, 1, 1, 1, 0, 1, 1, 1. Each one of those is just the prior number plus 1. So addition and counting partake of the same sort of spirit, okay? So here's what we're going to do. We're going to build a circuit to actually do that. And then it turns out, because of the nature of binary addition, we can add any 2 binary numbers. Actually, it turns out we can add 3 binary numbers. We can actually add 3 binary numbers. Think about that for a second. Well, it'll make more sense when I show it to you. But just be thinking about it, just so your brain starts to melt into slag. And by the way, can I just say, ice pack's working really well. Last time, my biggest fatigue, not to get overly graphic, but was over here. And because that's where all the nerve stuff comes right out of the spine, you know what I mean? It's just that kind of approximately the buttocks region. And that was really, really hurting by the end of lecture. And working the cold packs is definitely, I recommend it to you in similar circumstances. Also, can I just say this as an interlude? Some of you mentioned last time being on things like gabapentin for nerve pain. I had a really amazing epiphany 2 nights ago going into my night, because the nights were really hell. The days were tolerable and the nights were freaking hell. If any of you are in that chronic pain space, I'd love to share. I came across an epiphany and wound up 2 nights ago spending a night with really the same pain, same level of pain, but 8 hours of pain-free sleep at the same time. But by virtue of doing a crap ton of research and trying to understand a handful of things. It's obviously off topic for class, but some people mentioned last time when I brought up, being on a med like gabapentin. If you're dealing with chronic pain, I'd love to we can jump on a chat and I can share what I went through and what the experience was, if that's helpful to anybody, because it was quite unusual for me. And when I was done, it really was like a freakish game changer for me. And I'd been in the, night of the living hell pretty much night after night after night. And then for the last 2 nights, I've actually had pretty great nights. But the pain hasn't diminished. It's not because the pain went away. We can talk. So if that's interesting, ping me, DM me. We can jump on a chat sometime. I just love to share what I went through in case it has some value, to anybody. Because I feel like I did kind of crack the nut just a little bit on a few things. Even though, anyway, that's probably enough said. I'm not like the king of chronic pain, but this has been an interesting experience. All right, we call this thing a full adder. Why do we call it a full adder? I don't even know. I think it's because I can build a little circuit to just add 2 bits together. The full adder says I'm going to string a bunch of these together, like 8 of them, or 16 of them, or 32 of them, depending on your architecture. And it's a logic circuit. It's got 3 inputs, okay? And I'm going to show you the notation on this. It's got A and B and a carry. Now, when we do addition, right, what's 9 plus 3? Right? Slow ball on you here. 9 plus 3, you're like, poof, 12. Right. But what do you actually do there? You told me 12, but when you write it down, it's 1, 2. 9 plus 3 is 1, 2. Weird, right? I mean, you already know it in our normal way of thinking about math. 9 plus 3 is 12. You're overthinking this thing. No, you just said that 9 plus 3 equals 1, 2. That's what you said. Now, we have a name for 1, 2. We call it 12. But when you separate it apart, you actually said 1, 2. What you actually did was you said that 9 plus 3 is actually 2 carry the 1. Right? You carried 1. In other words, I had a 2 and a leftover 10. And so I put the leftover 10 up in the tens column. Right? So then there was nothing there in the tens column, just, empty. And then that dropped down and I got 1, 2. Okay? 1 10 and 2 digits, 2 1s and 1 10. Okay? And I know you already, it's not like I don't think you know this. I'm trying to break that down and it's like, the fish doesn't know that it's swimming in water. We get into these weird blind spots in our lives in learning because we don't, it just is what it is. You got to pull back and think about more consciously what you did there. And when you break that down, I can now apply that to a different number system like base 2. But I got to break down what I did in base 10. That's very natural. So there are 3 inputs. We're going to call them A sub I. I don't know if you can read that really, really well. A sub I, B sub I, and carry sub I. I just refers to the column. Column 0, column 1, column 2, column 3, okay? Just again, it's algebra just to represent symbolically. And then there are 2 outputs from this operation. There is S sub I, which is the sum for that particular column, and the carry for the next column. Any carry goes to the next column. So S sub I and then carry sub I plus 1. And we're counting left. We're increasing, I goes bigger as it goes left, okay? Following the idea of least order bits to high order bits. Okay? Here's the truth table for a full adder, which is, for a single, the addition of 2 bits together. When A is 0 for a given column, when A is 0 and B is 0, and there's no carry coming into you from the other, from the column to your right, the answer is that the sum is 0 and there's no carry. Okay? The carry into the next column is 0. Everybody cool with that? If I've got 0 plus 0 and there's a carry, do I do stuff here? No. If I've got 0 plus 0 and there's a carry of 1, the answer is the sum for that column is going to be 1 and there's no carry, etc. Follow it the rest of the way. Keep going. Now, when you get down to the bottom, if I've got A is 1 and B is 1 and there's a carry in, doesn't that freak you out at first? To go like, oh dear, that's 3. What do I do? Well, it turns out we have a number in binary for 3. It's 1, 1. What does that really mean? It means 1 carry the 1 into the 2's column. So we actually can do that. So 1 plus 1 plus 1 is 1 carry the 1. That's as complex as it gets. 3 1s being added together is the most complex scenario, where you get a 1 as your sum and you have to, there's a carry. Okay, any questions to this point? Are there any questions? Trent, yeah, let's go, we'll DM on that. I'm going minimal opioids right now. And there's still some debate in my mind, you know, about whether I can go without any. I think I probably can. Whoa, did I just get a bunch of, you know, I really don't want a bunch of those messages to show up. I'll have to just got that. I don't know what that was all about. Okay, let me see. Any other, yeah, so June Lynn just hit me up. We'll jump on DM and I can tell you what I went through. Kind of share some of that story. Any questions so far about, you know, this whole thing, the idea of just adding in binary? Because I'm going to show you the circuits next, but you got to understand it conceptually. Okay, you have to understand it conceptually. That when you have 3 1s in a single column for binary addition, I can actually do that. The answer is 1 carry the 1. Okay, I'm going to keep going. Here we go. We're going to walk through all of these. We're going to walk through, there's 8 possibilities with 2 inputs. Sorry, there's actually 3 inputs. There's an A, and I think that I'm going to walk through, I think I've got, let me just check real quick. I think I have, crap. I think there's some stuff that, Walter, we got to make a note on this. I think there's some stuff where I would normally jump over to the whiteboard. I just realized it. Because like I said, I was rototilling everything and at the start of the semester until I went into surgery and then came out with this mystery pain leg thing. So I'll do a couple. I have the magic notebook. Remember social contract? Yeah. I have the magic whiteboard. I'll do some right here. Paradoxically, I do have, if you look behind me, that's a whiteboard right there. It has a curtain on it. So I can actually do like confidential business stuff or working on legal cases or whatever and brainstorm up there and then just throw the curtains over when I've got a broadcast. But the problem is that that's too far away until I've got a better video magic configuration over here. But I'm ready. Fat marker, whiteboard, and we're going to do some of it, dang it. In the meantime, how are we doing on time? 12:06. Doing good. And I can tell we're doing good because my whole back butt pain thing is being really, really manageable right now because I'm a genius with the cold packs. Look at me, I invented cold packs. I'm a genius. But when you see my tricked out walker, you'll know that I actually am a genius. All right, here we go. First instance, A is 0, B is 0. And by the way, I got to do this right now, actually. I realize I really got to do just an example of this is all we're talking about, okay? And again, Walter, really, truly make a note. This is something we've got to come back to. It's just that, right? I've got to do this problem. Well, Let's do it together. 0 plus 0 is 0. 1 plus 0 is 1. 1 plus 1 is 0, carry the 1. 1 plus 0 plus 1 is 0, carry the 1. Now that I did carry, I had 4 values coming in and I had 5 values coming out. We got to talk about that, okay? That can be viewed as overflow. It turns out in certain kinds of math, when you're using 2's complement notation, you actually don't care if there's an overflow out into the next carry bit. Weird, but true, okay? So this then becomes, let's call this column 0. I don't know if you can read that. Column 1, column 2, and column 3. That's pretty weak sauce right there on my graphics, okay? That's just columns 0, 1, 2, and 3. So when I talk about this first line, I'm saying that A sub 0 is 0 and B sub 0 is 0. And this is the carries are right up here, right? Effectively, there's no, the carry is 0. It doesn't do anything, okay? So this is carry sub 0, A sub 0, B sub 0. When I add them together, I get sum sub 0. And if there's a carry, it's carry for sub 2, for column 2. Does that make sense? That was not really great graphics. Not really great graphics, but I wanted you to get a feel for that idea, okay? I literally would always do that on the board when we were in person, and so it didn't make it into the slides. That is one of the differences, frankly. All right. When I got a 0 and a 0 and there's no carry, the answer is 0 and there's no carry. All right, there we go. Now check it out. Check out what we got here. This is actually an adder. So strange. But what's actually happening is I've got basically, what's this basically doing? What's going to happen? I've got these values that go, I've got no knots. It's all just open. There's a knot. If I count the knots as if we were counting from 0 to all ones, right? Which is 7. I go, there's 0, 0, 0, 1, 0, 1, 0, 1, 0, 0. Wait, sorry. I'm gonna start over. We're off the wrong track. 0, 0, 0, okay, which is actually corresponds to that. 0, 0, 1, that corresponds to the next row over here. 0, 1, 0, you see it's like I'm just counting. 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. All 7 possibilities are laid out. Each of them feeds an AND gate. This 0, 0, 0 pattern is going to cause this AND gate to light up, and it's going to cause all the others to shut down. Okay? And what's going on here? This one also just is a little funky because when it's all zeros, it's almost like we just sort of throw it away because everything is just going to stay zeros. In other words, these values are 0. If I throw that away, these values are 0. That's just a funky trick. You could also take this guy and pipe it in, you know what I mean? Add it over here, or, you know what I mean? Add it into the output so that, that's 0. But the reality is I blew all these away by having at least one of these be a 0 getting through. Blew up all these AND gates. So these 2 OR gates, the carry for the next column and the sum for the current column, they're zeros. I don't have to do anything to make them 0. So I basically just ignore the output in that case. And the truth is, I don't even have to have this one selected. It doesn't even have to be there. You know what I mean? Because all that's going to happen is I'm going to blow everything up and it'll be zeros. It works. Funky little electronics trick. Okay, let's go. Next one. I got 0 plus 0, but there's a carry. What's my answer? I'm going to have a sum and a carry. So all I do again is I'm turning this AND gate on, and I turn all the others off. And I draw a line that pipes that into S, the sum. I don't do anything to C1 because it's already zeros. Okay, have the 1 goes into this OR gate so that S1 comes out as a 1 and the carry is 0. Are you tracking? Are you tracking with me? All right, let's keep going. Let's do the next one, which is A is 0, B is 1. All right, when A is 0, see the 0? That's a not, that turns that on. B is 1, and there's no carry. So if there is no carry, then this not turns that on. You get 1, 1, 1. Boom, that guy's on. And you just pipe it to wherever you want the thing to be. The output, you literally just pipe it to turn on any values. Okay, I'm going to speed it up a little bit now. 0, 1, 1. A is 0, B is 1, and there's a carry. So which one turns on? This one here. We're going to walk through. It's going to step through. This one is the one. There's, the not goes, that needs a 0 to turn on. These just have to be 1 so you can see it matches. This guy turns on. I run the line over here just to carry. So only carry gets a 1. Okay? And the S is off. Next one, basically the same idea. No, it's not the same idea. I'm a doof. A is 1, B is 0. It's going to turn on this gate. That's going to activate this OR gate, and you're going to get a 1, and the carry is still a 0. That's the right answer over there. Okay, 1, 0, 1 turns this one on, and we already know that it makes carry 1, and the sum needs to be 0. And then there's this one again, 1, 1, 0. This is the only AND gate. So this is basically kind of like a big, what is this? It's kind of a big decoder, And based upon what the 3 values are, I just map those to one of the 2 OR gates or both. So check this one out. When it's 1, 1, 1, only this AND gate works, right? There's no not, so it has to be 1, 1, 1. This guy turns on. That line comes, and I'm going to split the line, which I can do, and I'm going to turn on S1, and I'm going to turn on C, the carry for the next column over. Okay, that's our circuitry. All right, and all we're doing is basically just using the same kind of decoder that we were already doing. Cool, right? The answer is yes, Dr. K, it is cool. Okay. The next thing we do is we kind of put a little box around it. Now we're back to those Turing boxes, okay? Back to the Turing boxes. And we're just going to put a box around it and just go A, B, and C on the outside and the carry and the sum popping out the outside. Then we just like obscure it. So this is a way of the way we think about circuitry. You build the little grunge and you put a box around it, and then you just have inputs coming into the box. And that's kind of like a black box, kind of like a Turing black box. Stuff's coming in, stuff's going out. What's inside, you don't care. Okay. Okay, good. Best comment so far, Junlin. I'm very suspicious of the fact that you're understanding. Yeah. Well, don't worry. It'll go away. It'll betray you before we're done. And it's good though. Actually, it's a really good start. Then there's the part where you've got to kind of own it on your own terms. You know what I mean? Where later on you've still got it. And it's not just because I'm talking and it's clicking, but it's because you really do understand it. Sometimes the best way, by the way, is to find some victim that you're willing to explain it to. Like, can I just explain to you how this thing works? in the explaining, there is a reinforcing of the learning. Now what I can do is I can take these boxes, because I don't care about all the crap inside at this point. I can take these boxes, I can string them together and make a multi-bit adder, right? So I start with a default of 0 as the carry. There's A and B, A sub 0 and B sub 0. Now notice this time I'm putting the numbers 0, 1, 2, 3, okay? No carry initially. And A and B sub 0, it produces S sub 0, then it produces the carry for number 1. And then we just pipe it right over there. Just run a little wire, joinky. Now we take A1 plus B1 plus C1, and when we're done, we get S1 and a C. And all we're doing is that, but it's inside each one of these little boxes. All right, there we go. And that is a circuit for adding any two binary numbers, 4-bit. Cool? I think it's cool. A ripple carry, Texas. What is the technical difference of a ripple carry versus? This is a serious question, because I don't know the difference between a ripple carry and a carry. And also, I don't know, Texas. Are you like a computer engineering major? You know, again, all sincere questions. Studying electrical engineering, great. Yeah, no, anything if you got about this idea of technically calling it a ripple carry, because again, I'm not an electrical engineer, never have been. I'm not really a computer engineer to the extent that I am. You know, I don't know. Maybe I'm a hack. That's not strictly true, but you know what I mean. I don't feel as qualified as folks that are just constructing circuits all day long, you know, and really living in this place, you know. Okay, I'm going to keep going. Now, this one, by the way, the next picture, do not freak out. This is just to give you an example. There's a term that shows up especially in electrical engineering, which is a programmable logic array. Okay, all this is trying to do is say that you can just make all kinds of logic functions for any number of inputs, A, B, C, right? Have those pump in to this set of connections that are all black box to you, and then map them out in any combination you feel like. You could create, you know, whatever, the lazy cat function. You could create, I just made that up there. I don't even know what that would possibly be. You know, and the lazy cat function says whatever, you know, whenever it's an even number, I turn on the color orange, or you know, it means I take any pattern for these inputs and I can just map them to outputs, and I can make my own logic to do anything, just like I can with an adder, and that's called programmable logic array. Okay, PLAs. All you have to do is just know what your truth table is. Okay, that's it. Let me see. I'm backing up here. June Lin is A1001. Are we over here? Is that June Lin? Is that what you're talking about? I assume back on the previous. Um, Alex, pull it together. Pull it together, man. Yeah, so June Lin's question was, is A100010? Now, I don't know that I understand the question, which might imply that the answer is no, or it may just imply that I don't understand the question. So would you mind just rephrasing that core question? Because right here we don't have any context. Just describes how it sort of fits together and how the carry kind of ripples out. And also, by the way, who was it? Texas? That you still owe me an explanation of ripple carry. Just saying. Just saying. So yeah, Junlin, give me a little more meat there that I can work with on answering that question. Let me see. So, okay, Junlin said it goes from A0, B0, and becomes a carry 1. Well, that's if there is a carry, right? Could be 0 in the carry. Then becomes a carry 1. Then you got carry 1, A1, and B1 becomes carry 2. Okay, let's go back to, no, fair enough, fair enough. Okay, let me go back to my whiteboard. And then this is the same problem that I was doing before, okay? And this is the carries. The carries are just, that's where I'm going to put the carries, if there are any, okay? So when I'm in the first one, I've got A0, which is 0. I got B0, which is 0, and a default of 1. Sorry, of 0, because it's column 0. So I put that's the 1, that's the 0 I'm given. That's A0, that's B0. And what I get is I'm going to populate 2 places when I do this action. I think, Junlin, what you're trying to do is, I think what you're trying to do is have everything moving through the carry. I think that's what you're doing. The reality is I've actually got 2 outputs, a sum and a carry, okay, a 1-digit sum. So 0 plus 0 plus 0 is 0 in the sum and 0 in the carry, okay? And I now have, if I animated this, which I really need to do, Walter, remind me, I need to animate this, right? And do it maybe in the slides. So in other words, I have a 0 down here as an answer, and this carry brings a 0 in as an input to this next circuit. I want to just say one thing, Texas. You said the carry ripples through the full adder. It does, but only like as you do each addition, right? Oh, yes, Junlin, yes. Those numbers are the column numbers. A sub 0, A sub 1, A sub 2 are just the column numbers. Sorry for that confusion. But let's keep going. Then I've got in the second black box over, A is 1 and B is 0. And when I add those together, the sum becomes 1 and there's no carry. So there's no carry up there. Same thing, 1 plus 1 plus 0 gives me a 0 in the sum and a 1 in the carry. And then 1 plus 0 plus 1 gives me again a 0 and a 1 in the carry. All right, does that help, Junlin? Does that help? And again, Texas, the ripple, I don't know. It ripples, it kind of cascades, but it only moves one at a time. Then that addition happens, right? And then there's a carry and a sum, and then it ripples at each operation, it ripples one more to the left. Okay. And so this kind of an operation tends to have to be done sequentially. You got to do the rightmost bit first to see if there's a carry. then you do the next, bit and see if there's a carry. And you kind of have to do it in that order from the right to the left. I don't know if it's possible. It might be. Maybe it's been done to do an adder in such a way that it's like in parallel, where it all just goes latch. I doubt it. But it doesn't mean that it doesn't exist, and may have been a cool problem. Okay, I'm going to keep moving. So I mentioned PLAs. I'm not going to talk about PLAs. Okay, no more PLAs. This is it. This is all I'm going to talk about. It's just meant to reflect the fact that I can create for any number of, you give me 128 different possible values, and I'm just going to have a bunch of things that might happen. And all I have to do is just create a decoder that has all of those, things, all the options, right? From 0 to 127. And it's going to turn one of those on, and I can run that line, and I can split it to any of the various options arbitrarily and make any function I feel like. That's it. Okay. I'm going to keep going. How are we doing time-wise? We're doing good. By the way, do I seem lower energy than normal, or do I seem normal? I did this new muscle relaxation med starting yesterday afternoon. I slept like a drunken brick. Really, slept like 12 hours and was pretty groggy. I think it's the med, but I don't want to feel like that in the middle of the day. So I'm feeling fairly normal. That's good. Just calibrating whether I'm dragging, because you can't see yourself. Everybody lacks objectivity about themselves, Okay, a brief interlude about logical completeness. This is never like a module thing, but it is interesting just to note that PLAs only have and, ors, and not gates, and you can build any logic circuit with a PLA. What does that suggest? Suggests that the set of gates and, or, and not is what they call logically complete, because if we only have those gates, we can build any truth table for any function whatsoever. Okay, that's really just an interlude. We talked kind of, basically about it last time. Okay, everybody cool? Decoders, multiplexers, adders. They're going to come back, by the way, before we're out of this thing. Everybody cool? I'm going to roll. I'm going to keep rolling. Basic storage. Yeah, what we haven't talked about to this point is like memory. How do you store stuff in memory? How do you do it? Right? Again, it's remarkable to me that with an AND gate, an OR gate, and NOT circuits, you can frickin' build everything. Your entire laptop, And you could also view it, if you wanted to, as like, everything you ever want to do. Like Fortnite is basically just a very complex set of and, or, and not gates. Same with Spotify. Same with anything. Checking your email. It's crazy. It's really, really crazy. Okay, let's talk about basic storage. We're going to go super rudimentary, but we're going to talk about how do you build memory. Yeah, that's right, man. Yeah, the floss dance. You can build what? Every other dance? Is that what you're going with? Is that where you're going with that, Texas? You can build every dance from the floss dance. Okay, here we go. We're diving in some more, diving deeper. For some of you, if this creates temptations to bail, Just want to encourage you to not bail, but you may have to do a slightly different bit of time management than you have in the past. A lot of times what I think that you wind up doing, and maybe it's habits learned from high school, is that you, pad adjustment, cooling units, engaged. I think sometimes going back to high school, you get in this mode where it's like, well, I did all the homework packets and therefore I'm totally prepared for whatever the exam is going to be. And the problem with this stuff is there's a lot of systems and languages here that have to do with their own fluency, right? You have to acquire fluency in these languages, just like if you were studying Italian, you would have to acquire fluency, which comes by taking time every day. You can't just like cram, a book on Portuguese in a day and then you speak Portuguese. It doesn't work like that. So one of the things I would recommend is you go back through and then you grab just my slides from Canvas and just do just my slides and walk through them yourself. Explain them to a friend, a victim. Explain them to yourself. Say them out loud. Work it. It'll come, and it'll become more fluent as you work it. I promise. Here's what we're going to talk about for the next 12 minutes. We'll see how far we get. RS latch, gated D-Latch, and registers. And these are the building blocks of computer memory. It's actually, I'm just blown away by the folks that created this. You know what I mean? Like that was a thing. They did it. Starting with and or and not are like, hey, you know what else you could do with this thing? You can add stuff or we can make memory. Crazy. All right, here we go. This is an RS latch. Notice it has only two types of gates. It's got an AND gate and it's got a NOT gate right there. Or you could view this and say that that's a NAND because the little NOT is on the output. So this is a NAND, or you could say it's two gates, an AND and a NOT. All right, here's what happens. And you'll actually see this put together into a memory here in a bit. Now, there's two lines coming in. One is called R, one is called S. Technically, they stand for reset, set, and reset. Okay? They stand for set and reset. And the idea here, let me back up. Okay. The idea here is we have a unit that we can use that will stay a certain value as long as power stays on to the system. It'll have a certain value and that value will hold as that value no matter what else is happening all around it. Okay? Now that value is going to be this top one, A. So right now this RS latch has a value of 1. Okay? It has a value of 1. And because of the nature of an RS latch, it actually doesn't care about S and R, but they do need to both be on. When S is on and R is on, this thing is latched and it's stable, and the value of A just stays. Okay? With me so far? And B, we really don't care about. You often see these things drawn with B not even noted. We're just like this value just loops, comes out and loops back around to B. Okay, I want to just track this for a second. Look at this and see and try to prove to yourself or demonstrate to yourself that you believe this. We call this the quiet state or the stable state. A is 1, so let's just look at it. S comes into this AND gate, right? B is currently 0, So the value of this guy goes 0, but then it hits the not, turns into a 1, and A's 1, right? A then also splits and comes back around to here. R is on, and the R and the A together are both on, so this guy becomes 1, hits the not, flips it to off, so B is off, and here comes B, back around to here with a 0 right here, okay? On, ANDed with off is no, hits the not, goes yes, flips, and you can just chase your tail. You can chase your tail. And what you can prove to yourself is as long as S and R are both on, this thing is stable. And the value of A is going to just stay 1. Okay? Cool? But here's the trick. Here's the trick. Now this is where set and reset come into play. I'm going to fiddle with the R line. Okay? I'm going to fiddle with the R line. Because what reset means is I'm going to change the value of this circuit to be 0. When you do S, it changes the value to be 1. When you do R, it changes the value to be 0 of A, which is the value coming out of this circuit. Okay? For now, just understand that if I fiddle around with S, I'm setting it, therefore 1. If I fiddle around with R, I'm resetting it, aka making it 0. Okay? But here's how I fiddle around. This is what I do to fiddle around. I start by clearing R. So I just did that. I made R a 0. When I do that, B changes to 1. Watch it, watch it. R goes 0, A is 1, value's no. I nod it, yes. B is now on. Now let's loop it, let's keep going. B comes into this circuit, S and B, they're both on, which means that's a 1, hits the not, 0. Okay? Now, keep going. 0 ANDed with 0 is 0, hits the not, stays on. 1 and 1 is 1, hits the not, goes 0. You can then run it a couple times and convince yourself it's not going to change. And then I set R back to 1 again. The stable state is that S and R are both on. That's the stable state. And I just changed the value of this circuit to be 0 when it was 1. Interestingly, if I do the reset again by turning R off while we're in that condition, it doesn't hurt anything. You know, if it was 0 and I do a reset, it'll just stay 0. If it was a 1 and I do a set, it'll just stay 1. Okay, let's do the other one, and then we'll be about out of time. Is this popping anybody's head? Is this, let me see. Is it technically an RS NAND latch? You mean an RS latch, Texas, an RS latch built with a NAND gate? I think the answer is yeah. I think that is a NAND gate. You can look at it as a NAND gate. It functions. I mean, I think that's probably the right notation, because you let the values come in without changing them. You do what you do with an AND, and then you flip it. So yeah, that's a NAND gate. Okay, let's do the other one. We're going to set it now. In order to set it, so if I want to reset, I take R down, I wait for a second, and then I turn it back on. If I want to set it, I push S down to 0, let it hum for a second, and then take S back to on. That's how I'm like, make it a 0, make it a 1, make it a 1 again, make it a 1 again, make it a 0, make it a 0. As long as I can control R and S, I can cause this circuit to make A whatever we want it to, to make it either a 0 or a 1. Let's do it. S goes to 0, which is we're fiddling with S now because we want this value back to be 1. I clear S. And when I do that, A changes to 1. Check it out, right? There it is. I got 0 and 1. That's going to be 0. I nod it. Boom. A is now on. Loop around A over here. A is 1 and R is 1. That means yes. I hit the not. Boom. Nope, that's 0. B is now 0. Here comes B, 0, and 0 is 0. I nod it, yes. 1 and 1 is 1. I nod it, 0. And you can see that it's stable. And now to get it all back, I then set S back to on, and I'm back in the quiet state, okay? And you might be like, well, why do I have to change S back, right? Because at that moment, everything stays fine. Everything's stable, right, with 1. The reason is because if I don't change S back, and now I just simply try to go fiddle with R, I screw everything up. I've got to have them both on to be stable, and one of them goes off, and that causes the change. So when I'm done, I got to put it back on. I got to make S and R back on. Thank goodness for cold packs. This really has been better. This has been easier on me physically today than it was 2 days ago. So, and I'm sure ongoing healing from the surgery is not hurting that at all either. Okay, that's it. That's the RS latch. I turn S off and back on, it makes A1. I turn R off and back on, it makes A0. That's it. Do you see how all of a sudden I've got this line and the line's a 0 or 1? I can string these things together and I can make memory. I got a string. All memory is a string of bits that I can get to somehow. And we're going to later on, we're about out of time, but we're going to, next week maybe, I'm going to show you, we're going to build a little memory that's only going to have 12 bits in it. It's going to have 4 memory locations, and each memory location has 3 bits. And it's small so we can like fit it on a page and not have to be crazy. But the principle is just scale. Where's this data coming from? Where's the data coming from? Well, the answer to that is right now we don't know. I am telling you that there's got to be some control circuitry that can turn S off and back on again, or that can turn R off and back on again based upon whether I'm trying to make this into a 0 or a 1. Pretty cool. And once again, if this just really floats your boat, like big time, you might want to be thinking about computer engineering and electrical engineering. It's not, I've talked before about, it's a myth to talk about, well, electrical engineers, if you're smart enough, you do EE. You're not quite as smart, then you do computer engineering. Then if you're less smart, you do CS. And if you're even less smart, you do information systems. No, that's bullcrap. It's not about how smart you are. It's about what you care about, what you like. Your brain's just kind of wired. That's the key with finding a major and what you want to study and what you want to do for a career is what's your brain wired to, to really want to do. That's the burning question. And some people's brains are really wired in. You get to this and it's just like nirvana. And for other people, it's like, oh, spare me, So you got to find that yourself, where you're at, what you really like. And then my experience is that anything you actually like, you can understand, period. And I think that's true. Now, what we're going to do, we're going to come back, teaser, D-Latch. What's the D stand for? Data. We're going to basically show you with this D-Latch, which encases an RS latch, okay, how to make that into a thing that can actually be data, okay? You got to have the controls to go up, down on the R and S. You got to have the ability on demand. That's what the gated D-Latch does. It gives you that next little bit of control. All right, we're out of time. Apologize for the late start today. I'm hoping, when are we back? Tuesday? Yeah, I'm going to keep recovering. That's my plan. I'll keep recovering. I'm going to get better all the time. And true to my promise, I'm going to keep wearing t-shirts as long as I'm wearing sweats. Now, when I get to the part where I'm actually putting pants on, I'll put a button down. You'll know I've arrived back to healing at some level when I'm in back here with a shirt with a collar and a button down. But anyway, yeah. Oh, Cure for Speed, Matthew, the kittens, the feels. I need a kitten right now. Seriously, I do. Anyway, C said, I think there's only 2 to 3 different classes between electrical engineering and computer engineering. I think it's a little more extreme than that. I think the math and other sorts of that kind of requirements are different. But it's not that different. But anyway, again, thanks, Gabe. Thanks for everybody again. Thanks for the good wishes. If you want to talk about chronic pain, DM me, okay? And we can have some of that conversation about what I went through and what I feel like I learned, a little bit of the revelation that I kind of went through on that. But hopefully, and you guys, please keep up. I beg you, right? I beg you. If you bail, you fail. Don't fail. Don't bail. Don't fail. So, all right. Thanks, everybody. I'm getting better. I'm going to shut down the stream.